Imagine, for a moment, that you are standing at the eyepiece of a telescope. Not a backyard telescope, but one of the great instruments of the mid-20th century. A radio telescope scanning the sky from a quiet observatory somewhere in the northern hemisphere. The year is 1957. The space age has barely begun. Sputnik has just been launched. Humanity is only starting to understand how vast the cosmos really is. And on this particular night, among the thousands of faint signals being catalogued from across the sky, one object catches your attention. It appears to be nothing more than a dim point of light, a faint smudge lost among billions of other faint smudges in the constellation Canes Venatici, the hunting dogs. You note its position, record its brightness, and move on. There is no reason to think it is anything special. There is no reason to think it is anything more than a distant star or perhaps a small, unremarkable galaxy. You have no way of knowing that this tiny point of light is one of the most powerful objects in the entire observable universe. You have no way of knowing that behind that faint glow lies a monster so vast, so massive, so profoundly beyond anything else ever discovered, that it will take decades of technological advancement before humanity can even begin to comprehend what it truly is. That object was catalogued simply as TON 618. And tonight, we are going to take a very long, very gentle journey into the heart of that monster. But before we get there, let us take our time. Let us start from the very beginning. Because to truly appreciate the scale of TON 618, we first need to understand the universe it lives in, the forces that created it, and the extraordinary chain of discoveries that led us to it. The story begins, as so many stories in astronomy do, with light. Everything we know about the universe beyond our own planet comes to us in the form of light. Not just visible light, the kind your eyes can see, but the entire electromagnetic spectrum, from the longest radio waves stretching across kilometers to the shortest gamma rays smaller than the nucleus of an atom. When astronomers point their telescopes at the sky, they are not seeing the universe as it is right now. They are seeing the universe as it was when the light left its source. A star that is 100 light-years away appears to us as it was 100 years ago. A galaxy that is 1 billion light-years away appears to us as it was 1 billion years ago. And an object like TON 618, which sits roughly 10.4 billion light-years from Earth, appears to us as it was 10.4 billion years ago, when the universe itself was only about 3.3 billion years old. We are looking back in time to an era when the cosmos was still young, still forming, still assembling the great structures of galaxies and clusters that we see around us today. And yet, even in that young universe, something extraordinary had already taken shape. Something had already grown to a size that, even today, pushes the limits of what physics tells us should be possible. When TON 618 was first catalogued, no one understood what it was. In the 1950s and 60s, astronomers were still working out the basic geography of the cosmos. They knew that the Milky Way was a galaxy, one of many. They knew that galaxies came in different shapes and sizes, spirals and ellipticals and irregulars. They were beginning to measure the distances to these galaxies using a variety of techniques, from the brightness of certain types of stars to the redshift of their light. Redshift is a crucial concept, so let us pause here for a moment. When an object in space is moving away from us, the light it emits gets stretched out as it travels. The wavelengths become longer, shifting toward the red end of the spectrum. This is similar to the way the pitch of a siren drops as an ambulance drives away from you. The faster an object is receding, the more its light is redshifted. And because the universe is expanding, with distant galaxies moving away from us faster than nearby ones, the amount of redshift tells us how far away an object is. A small redshift means the object is relatively close. A large redshift means the object is very far away, and an extremely large redshift means the object is among the most distant things we can see. When astronomers finally measured the redshift of TON 618, they got a value of 2.219. For context, a redshift of 0 means the object is right here. A redshift of 1 means the object is roughly 7.7 billion light-years away. A redshift of 2.2 puts TON 618 at roughly 10.4 billion light-years from Earth. This was astonishing, because the object, which had appeared as nothing more than a faint point of light, was not faint at all. It was unbelievably, almost incomprehensibly bright. It only appeared faint because it was so incredibly far away. If you could somehow transport TON 618 to the distance of our nearest neighboring galaxy, the Andromeda Galaxy, which is only about 2.5 million light-years away, it would outshine every single star in the night sky. It would be visible in broad daylight. It would cast shadows on the ground at night. This was not a star. This was not an ordinary galaxy. This was something else entirely. In the early 1960s, astronomers had begun discovering a new class of objects that defied easy explanation. They looked like stars, appearing as compact points of light rather than the fuzzy extended shapes of galaxies. But their redshifts placed them at enormous distances, which meant their luminosities were far beyond anything a single star or even a normal galaxy could produce. These objects were given the name quasi-stellar radio sources, later shortened to quasars. The word quasar has become so common that it is easy to forget what it represents. A quasar is not a type of star. A quasar is not a type of galaxy exactly. A quasar is the visible signature of something far more extreme. It is the blinding glare produced when matter falls into a supermassive black hole at the center of a galaxy. The black hole itself is invisible, but the material spiraling into it, heated to millions and billions of degrees, compressed and accelerated to nearly the speed of light, releases so much energy that it can outshine the entire galaxy around it. Sometimes, by factors of hundreds or thousands, the galaxy fades into insignificance. All you can see is the blazing core. That is a quasar, and TON 618 is among the most luminous quasars ever discovered. Its total energy output is estimated at roughly 140 trillion times the luminosity of our Sun. Let that number settle for a moment. 140 trillion. Our Sun is already an extraordinary object, a ball of hydrogen and helium 1.4 million kilometers across, fusing 600 million tons of hydrogen into helium every single second, releasing enough energy to power the entire Earth thousands of times over. And TON 618 outshines the Sun by a factor of 140 trillion. To put it another way, if you gathered together every star in the Milky Way, all 100 to 400 billion of them, and added up their combined light, TON 618 would still be brighter, by a significant margin. It is not just bright, it is one of the brightest persistent objects in the observable universe. But luminosity is just the beginning of what makes TON 618 remarkable. Because luminosity is a consequence. It is the effect, not the cause. The cause, The engine driving all of that unimaginable energy output is the black hole at the center. And when astronomers estimated the mass of that black hole using the width and velocity of the gas clouds orbiting around it, they arrived at a number that made even seasoned astrophysicists pause. 66 billion solar masses. Let us make sure that number is clear. One solar mass is the mass of our Sun, which is already an almost incomprehensibly large object. The Sun contains 99.8% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust orbiting the Sun, all of it together makes up only 0.2% of the total. The Sun alone is roughly 330,000 times more massive than the Earth. And the black hole at the center of TON 618 contains the equivalent of 66 billion of those suns. Not 66 million, not 6.6 billion, 66 billion. It is one of the most massive single objects ever discovered in the observable universe. It is not merely large, it is in a category that some scientists have proposed deserves its own name. Not just supermassive, like the black holes found at the centers of most galaxies, but ultramassive. A word reserved for black holes so large that they strain our understanding of how such objects could have formed in the first place. And that is the question that has haunted astronomers ever since the true nature of TON 618 was understood. How did it get so big? How did 66 billion solar masses of material end up compressed into a single point in space? What sequence of events, what chain of cosmic accidents and processes could have built something so enormous in a universe that was, at the time we are observing it, only 3.3 billion years old? To answer those questions, we need to understand what black holes are, how they form, and why some of them grow to sizes that seem almost impossible. So let us go deeper. Let us peel back the layers of this mystery, one by one, gently and carefully. There is no rush. The universe has been here for 13.8 billion years. TON 618 has been sitting in its corner of the cosmos for over 10 billion of those years. It will still be there when we are done. For now, close your eyes if you like. Let the numbers wash over you. Let the scale of things settle into your mind like snow falling on a quiet field. We have a long journey ahead of us, and the deeper we go, the stranger things become. The universe, for all its apparent complexity, operates on a surprisingly small number of fundamental forces. There are 4 of them. The strong nuclear force, which holds the nuclei of atoms together. The weak nuclear force, which governs certain types of radioactive decay. The electromagnetic force, which governs the interactions between charged particles and gives us light, electricity, magnetism, and chemistry. And gravity. Gravity is by far the weakest of the 4 forces. If you hold a refrigerator magnet in your hand, the electromagnetic force in that tiny magnet is strong enough to overcome the gravitational pull of the entire planet Earth. In everyday life, gravity seems barely relevant. You can jump. You can lift things. You can throw a ball into the air and watch it come back down. Gravity is gentle. Gravity is patient. Gravity is easy to overcome. But gravity has one property that the other forces do not. It is always attractive, and it has unlimited range. The electromagnetic force can be both attractive and repulsive. It can be shielded and canceled out. The nuclear forces only operate over incredibly short distances, smaller than an atom. But gravity reaches across the entire universe. Every particle of matter in the cosmos pulls on every other particle of matter. no matter how far apart they are. The pull gets weaker with distance, fading with the square of the separation, but it never reaches zero. It never turns off. It never stops. And because of this, over very long timescales and very large accumulations of mass, gravity becomes the dominant force in the universe. It is gravity that pulls clouds of gas together to form stars. It is gravity that holds galaxies together. It is gravity that shapes the large-scale structure of the cosmos, the vast web of filaments and voids that stretches across billions of light years. And it is gravity that creates black holes. A black hole is what happens when gravity wins completely. When an object becomes so dense, so compact, that the gravitational pull at its surface becomes stronger than any force in the universe can resist. Not even light, the fastest thing in existence, can escape. The boundary around a black hole where the escape velocity equals the speed of light is called the event horizon. It is not a physical surface. There is no wall, no barrier, no membrane that you would bump into. It is simply a mathematical boundary, a point of no return. Once you cross it, no signal, no particle, no information of any kind can ever travel back out. Whatever falls past the event horizon is gone from our observable universe forever. The concept of an object so dense that light cannot escape from it was first proposed in the late 18th century by the English clergyman and natural philosopher John Michel, and independently by the French mathematician Pierre-Simon Laplace. They imagined what they called dark stars, objects so massive that their gravitational pull would prevent light from leaving. But their reasoning was based on Newtonian gravity, which treats light as a particle affected by gravitational force in the same way as a cannonball. The modern understanding of black holes comes from Albert Einstein's general theory of relativity, published in 1915. General relativity describes gravity not as a force that pulls on objects, but as a curvature of spacetime itself. Mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. In this framework, a black hole is a region where spacetime is curved so severely that all paths, even the paths of light, curve inward and lead to the center. The first exact solution to Einstein's equations describing a black hole was found in 1916 by the German physicist Karl Schwarzschild, remarkably while he was serving on the Eastern Front of the First World War. The Schwarzschild solution describes the simplest possible black hole, one with mass but no charge and no spin. It predicts the existence of an event horizon at a specific radius from the center, now called the Schwarzschild radius. For an object with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. This means that if you could somehow compress the entire mass of the Sun into a sphere only 6 kilometers across, it would become a black hole. For the Earth, the Schwarzschild radius is about 9 millimeters. You would need to crush our entire planet into a marble smaller than a centimeter to turn it into a black hole. For Ton 618, the Schwarzschild radius is approximately 1,300 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometers. So, the event horizon of Ton 618 stretches roughly 1,300 times farther from its center than the Earth is from the Sun. That is a radius of about 195 billion kilometers. The diameter, from one side of the event horizon to the other, is roughly 2,600 astronomical units. To help you visualize this, our entire solar system, from the Sun all the way out to the orbit of Pluto, spans roughly 80 astronomical units in diameter. The event horizon of TON 618 is more than 30 times wider than our entire solar system. You could place our solar system inside the event horizon of TON 618, and it would be lost like a grain of sand inside a cathedral. This is the scale we are dealing with. This is the kind of object that sits at the heart of the quasar, known as TON 618. And this is only the beginning of what makes it so extraordinary. But before we explore the full scale of TON 618 and the quasar it powers, let us first understand how black holes form in the natural universe. Because black holes do not simply appear. They are not placed into the cosmos by some external hand. They are born from the deaths of stars, from the collisions of galaxies, from the slow, patient accumulation of matter over billions of years. And the story of how a black hole grows from a relatively modest beginning to a monster containing 66 billion solar masses is one of the most fascinating and still partially mysterious stories in all of astrophysics. Section 2. How black holes are born. Stars are born in clouds of gas and dust called nebulae. These clouds are vast, sometimes spanning dozens or even hundreds of light years across. They are cold, with temperatures only a few degrees above absolute zero, and they are very, very tenuous, with densities far lower than the best vacuum we can create in any laboratory on Earth. But they are not empty. They contain hydrogen, the simplest and most abundant element in the universe, along with smaller amounts of helium and trace quantities of heavier elements forged in the hearts of earlier generations of stars. And within these clouds, gravity is at work. A slight increase in density in one region of the cloud, perhaps caused by the shock wave from a nearby supernova or the gravitational influence of a passing star, begins to pull surrounding material inward. As more matter accumulates, the gravitational pull grows stronger, drawing in even more material. The cloud begins to collapse. As it collapses, it heats up. The gravitational energy of the infalling material is converted into thermal energy, raising the temperature of the gas. The cloud contracts further, grows hotter, and begins to glow. At its center, a dense core forms, growing denser and hotter with every passing moment. This is a protostar, an object on its way to becoming a true star but not yet there. For a protostar to become a star, it needs to reach a critical threshold. The temperature and pressure at its core must become high enough to ignite nuclear fusion, the process by which hydrogen nuclei are forced together to form helium nuclei, releasing enormous amounts of energy in the process. This requires a core temperature of roughly 10 million degrees Celsius. When that threshold is crossed, fusion begins, and the energy released creates an outward pressure that balances the inward pull of gravity. The object stabilizes. It becomes a star, and it will continue burning hydrogen in its core for as long as the fuel supply lasts, which, depending on the mass of the star, can be anywhere from a few million years to tens of billions of years. Our Sun is a middle-aged star of moderate mass. It has been burning hydrogen for about 4.6 billion years, and will continue to do so for roughly another 5 billion years. It is not massive enough to end its life as a black hole. When it exhausts its hydrogen fuel, it will swell into a red giant, shed its outer layers into space, and leave behind a small, dense core called a white dwarf, about the size of the Earth but containing roughly the mass of the Sun. A white dwarf is supported against further collapse not by nuclear fusion, but by a quantum mechanical effect called electron degeneracy pressure. The electrons in the white dwarf resist being compressed any further, holding the object up against gravity. This works, but only up to a point. There is a maximum mass for a white dwarf, discovered in the early 20th century by the Indian astrophysicist Subramanian Chandrasekhar. That limit, now called the Chandrasekhar limit, is about 1.4 solar masses. A white dwarf more massive than this cannot be supported by electron degeneracy pressure. If more mass is added, it will collapse further. Stars significantly more massive than the Sun live much shorter lives. They burn through their fuel far more quickly, not because they have less fuel, but because they burn it at a furiously accelerated rate. A star 10 times the mass of the Sun might exhaust its hydrogen in only 20 million years. A star 50 times the mass of the Sun might last only a few million years. These massive stars do not end their lives quietly. When they run out of fuel, they undergo a catastrophic gravitational collapse. The core, no longer supported by the outward pressure of nuclear fusion, implodes in a fraction of a second. The outer layers of the star, no longer held up, come crashing down and then rebound outward in a titanic explosion called a supernova. A supernova is one of the most violent events in the universe. For a brief period, a single exploding star can outshine an entire galaxy containing hundreds of billions of stars. The explosion flings the outer layers of the star into space at speeds of tens of thousands of kilometers per second, enriching the surrounding gas with heavy elements like carbon, oxygen, iron, and gold. Everything heavier than hydrogen and helium in your body was forged in the heart of a massive star and scattered into space by a supernova billions of years ago. But the core remains, and what happens to that core depends on its mass. If the core is between roughly 1.4 and about 2.5 solar masses, it collapses into an object called a neutron star. A neutron star is supported not by electron degeneracy pressure, but by neutron degeneracy pressure and the strong nuclear force. It is an object typically only about 20 kilometers in diameter, the size of a small city, but containing more mass than the Sun. A single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. Neutron stars are among the densest objects in the universe. They spin at incredible rates, sometimes hundreds of times per second. They have magnetic fields trillions of times stronger than Earth's. They are extraordinary objects in their own right. But if the collapsing core is more massive than roughly 2.5 to 3 solar masses, even neutron degeneracy pressure cannot hold it up. There is no known force in the universe that can prevent further collapse. The core continues to shrink, growing denser and denser, until all of its mass is compressed into a single point of infinite density called a singularity. An event horizon forms around it. A black hole is born. This moment, the birth of a black hole, is one of the most dramatic events in the universe. In less than a second, a region of space that was filled with dense nuclear matter transforms into something entirely different. A sealed region of space-time from which nothing can escape. The event horizon snaps into existence like a closing door, and behind that door, the matter continues to fall inward, piling up at the center in a state that our current theories cannot fully describe. General relativity predicts a singularity, a point of infinite density and zero volume, where the known laws of physics break down. Whether a true singularity actually exists, or whether some as yet unknown quantum gravitational effect intervenes to prevent it, is one of the great open questions in physics. What we do know is that from the outside, the black hole is deceptively simple. It is described entirely by just three numbers: its mass, its electric charge, and its spin. Everything else about the original star, its chemical composition, its temperature profile, its magnetic field structure, its history, all of that information is hidden behind the event horizon, inaccessible to the outside universe. This remarkable simplicity is captured in a famous phrase coined by the physicist John Wheeler: "Black holes have no hair," meaning that two black holes with the same mass, charge, and spin are identical, regardless of how they formed or what they consumed. These are called stellar mass black holes because they form from the death of individual stars. They typically range in mass from about 3 to roughly 100 solar masses. They are found scattered throughout galaxies, often in regions where massive stars have recently lived and died. Some of them are detected through their gravitational influence on nearby companion stars, pulling streams of gas from the companion and heating that gas to X-ray temperatures as it spirals inward. Others have been detected through gravitational waves, ripples in space-time produced when two black holes spiral together and merge. The first direct detection of gravitational waves, announced in February 2016 by the LIGO collaboration, came from the merger of two stellar mass black holes, each about 30 solar masses, roughly 1.3 billion light-years from Earth. Stellar mass black holes are remarkable, but they are small compared to the monsters that lurk at the centers of galaxies. Those are the supermassive black holes, objects ranging from hundreds of thousands to billions of solar masses. And TON 618, at 66 billion solar masses, sits at the extreme upper end of this range. Every large galaxy in the universe appears to harbor a supermassive black hole at its center. Our own Milky Way has one. It is called Sagittarius A star, and it has a mass of roughly 4 million solar masses. That sounds enormous, and it is, but compared to the total mass of the Milky Way, which contains roughly 1.5 trillion solar masses of material, including dark matter, Sagittarius A star is tiny. It is like a single grain of sand sitting at the center of an enormous beach. Yet, despite its relatively modest mass, Sagittarius A star has played a crucial role in the formation and evolution of our galaxy. Its gravitational influence shapes the orbits of stars in the galactic center. Periodic outbursts of energy from material falling into it have sent shock waves through the surrounding gas, influencing where new stars can form. The black hole at the center of the galaxy Messier 87, known as M87 star, is about 1,600 times more massive than Sagittarius A star, weighing in at roughly 6.5 billion solar masses. M87 star became the first black hole ever directly imaged when the Event Horizon Telescope collaboration released its iconic photograph in April 2019, showing the dark silhouette of the event horizon surrounded by a bright ring of superheated plasma. That image was a milestone in the history of science, the first time humanity had ever seen a black hole with its own eyes. And yet MEM 87 star, enormous as it is still roughly 10 times less massive than TON 618. This raises a profound question. How do supermassive black holes form? If stellar mass black holes are born from the deaths of individual stars, and they top out at maybe 100 solar masses, How do you get from 100 solar masses to 4 million, or 6.5 billion, or 66 billion? What bridge connects the death of a single star to a monster that outweighs entire galaxies? This is one of the great unsolved problems in astrophysics, and there are several proposed answers, none of which are fully proven. Let us walk through the main ideas, because understanding how supermassive black holes might form is central to understanding what TON 618 is and why it matters. The first and most straightforward idea is simple growth through accretion. A stellar mass black hole forms in the usual way, from the collapse of a massive star. It then gradually grows by consuming surrounding gas, dust, and occasionally other stars. Over billions of years, it swallows enough material to become supermassive. This idea is appealing in its simplicity, but it runs into a serious problem: time. There is a maximum rate at which a black hole can swallow material, known as the Eddington limit. The Eddington limit arises because as material falls toward a black hole, it heats up and radiates energy. That radiation pushes outward on the infalling material, creating a kind of pressure that opposes further accretion. If the black hole tries to eat too fast, the radiation pressure blows the incoming material away. The Eddington limit sets a maximum growth rate, and when you do the math, starting from a stellar mass black hole of, say, 10 solar masses, and growing at the Eddington rate, it takes a very long time to reach billions of solar masses. Longer, in some cases, than the age of the universe at the time we observe these objects. We see quasars powered by supermassive black holes at redshifts of 6, 7, and even higher, meaning we are seeing them when the universe was less than 1 billion years old. There simply is not enough time for a small seed black hole to grow to billions of solar masses by eating at the maximum rate. Something else must be happening. One possibility is that the seed black holes were much larger to begin with. Instead of starting from the collapse of a single star, perhaps the first supermassive black holes formed from the direct collapse of enormous clouds of primordial gas in the early universe. In the right conditions, a massive cloud of hydrogen, if it avoids fragmenting into individual stars, could collapse directly into a black hole with a mass of tens of thousands or even hundreds of thousands of solar masses. This gives the growth process a huge head start. Starting from a seed of 100,000 solar masses instead of 10, the time required to reach billions of solar masses becomes much more manageable. This is called the direct collapse black hole scenario, and it is a leading candidate for explaining how the earliest supermassive black holes formed. Another possibility involves mergers. Black holes can grow not only by swallowing gas, but by merging with other black holes. When two galaxies collide, which happens frequently over cosmic time, the supermassive black holes at their centers can eventually spiral together and merge, forming a single, more massive black hole. Through repeated mergers over billions of years, a black hole can grow enormously. This process is expected to produce gravitational waves at very low frequencies, which future space-based gravitational wave detectors like LISA may be able to detect. A third possibility, and one that has gained increasing attention in recent years, is super-Eddington accretion. The idea that, under certain conditions, black holes can eat faster than the Eddington limit would normally allow. If the infalling material is dense enough and arrives from the right geometry, the radiation can be trapped within the flow and carried inward along with the matter, rather than escaping and pushing the material away. This allows the black hole to grow at rates several times or even tens of times above the classical Eddington limit. Super-Eddington accretion may have played a role in the rapid growth of the earliest supermassive black holes. There is one more growth mechanism worth mentioning, though it is more speculative. Some theorists have proposed the existence of primordial black holes that formed not from the collapse of stars but from extreme density fluctuations in the very early universe, within the first fraction of a second after the Big Bang. If regions of space were dense enough during those earliest moments, they could have collapsed directly into black holes before any stars or galaxies had formed. These primordial black holes could have had a wide range of masses, from tiny objects smaller than an atom to massive seeds thousands or millions of times the mass of the Sun. If primordial black holes of large mass existed, they would have had a significant head start on growth, sitting at the centers of the first dark matter halos and accreting material from the very beginning of cosmic structure formation. This remains a highly speculative idea, and there is currently no direct evidence that primordial black holes of large mass exist. But it is one possible piece of the puzzle, and it illustrates how creative nature might be in finding ways to build the monsters we observe. In reality, the growth of a monster like TON 618 probably involved all of these mechanisms. It may have started as a large seed, perhaps from a direct collapse event in the early universe. It then grew through vigorous accretion, possibly exceeding the Eddington limit at times, and it almost certainly experienced multiple mergers with other black holes as its host galaxy collided and merged with other galaxies over billions of years. The result, after billions of years of growth, is an object containing 66 billion times the mass of the Sun, an object so massive that it warps spacetime across a region larger than our entire solar system. An object whose gravitational influence extends across hundreds of thousands of light years. TON 618 is not just big. It is the end product of billions of years of cosmic evolution, the accumulated gravitational legacy of countless stars, gas clouds, and galaxies that fell into its embrace and never came back. And now that we understand, at least in broad strokes, how such an object might form, let us turn our attention to the full, staggering scale of what TON 618 truly is. Let us try, as best we can, to wrap our minds around the numbers, because the numbers, in this case, are the most eloquent testimony to the awesome power of gravity operating over cosmic time. Section 3. The impossible scale. Before we begin measuring TON 618, let us take a moment to appreciate why scale matters in this story. Human beings evolved to understand the world at a very specific range of sizes. We are comfortable with distances measured in meters and kilometers, with weights measured in grams and kilograms, with time measured in seconds and years. Our brains are wired for the savannah, for tracking prey across a few kilometers, for estimating the weight of a stone, for remembering the seasons. Nothing in our evolutionary history prepared us for numbers with 40 digits, distances measured in billions of light years, or timescales stretching across trillions of millennia. And yet, these are the numbers we must grapple with to understand what TON 618 truly is. So let us go slowly. Let us build our understanding piece by piece, comparison by comparison, starting with the most fundamental property of all. Let us begin with mass, because mass is the most fundamental property of a black hole. Everything else follows from it. The mass of TON 618's black hole has been estimated at 66 billion solar masses. We have said this number before, but let us now try to truly understand what it means. The Sun has a mass of approximately 1.99 times 10 to the 30th kilograms. That is a 2 followed by 30 zeros. Written out, it looks like this: 1,990,000 trillion kilograms. This is already a number far beyond everyday human comprehension. The entire Earth, every mountain, every ocean, every continent, the iron core, the rocky mantle, all of it, has a mass of about 6 times 10 to the 24th kilograms. The Sun is 330,000 times more massive. And Ton 618's black hole is 66 billion times more massive than the Sun. If you multiply it out, the mass of Ton 618's black hole is roughly 1.3 times 10 to the 41st kilograms. That is a number with 41 digits. There is no everyday analogy that can make this number intuitive. It is simply beyond the scale of anything in human experience. Let us try some comparisons. The Milky Way galaxy, our home, contains roughly 1.5 trillion solar masses of material, including all its stars, gas, dust, and dark matter. Ton 618's black hole alone, just the black hole, not the galaxy around it, contains about 4.4% of the mass of our entire galaxy. A single object, occupying a region of space that, while enormous by solar system standards, is still vanishingly small compared to a galaxy, contains nearly 5% of all the mass in the Milky Way. If you placed Ton 618's black hole at the center of our galaxy, replacing Sagittarius A star, it would be roughly 16,500 times more massive than the black hole currently sitting there. It would dominate the gravitational dynamics of the entire galactic center, dramatically altering the orbits of stars for thousands of light years in every direction. Let us try another comparison. Imagine you could line up suns, one after another, like beads on a string. Each sun is about 1.4 million kilometers in diameter. To represent the mass of Ton 618 in suns, you would need 66 billion of them. If you lined them up touching edge to edge, the line would stretch for roughly 92.4 trillion kilometers, or about 9.8 light years. That is more than twice the distance from our Sun to the nearest star, Proxima Centauri. A line of suns representing the mass of TON 618 would stretch across interstellar space, a bridge of stellar material connecting our solar system to its nearest neighbor and continuing far beyond. And all of that mass is compressed into a single object, a region of space-time from which nothing, not even light, can escape. Or consider it this way. The mass of Ton 618's black hole is roughly equivalent to the combined mass of 13 entire Milky Way galaxies, if you count only the ordinary visible matter in each galaxy, leaving out the dark matter. 13 galaxies worth of stars, gas, dust, and planets, all compressed into a single gravitational prison. The mind recoils from such numbers. But the numbers are real. Now let us talk about size. As we discussed earlier, the event horizon of a non-rotating black hole, the Schwarzschild radius, is directly proportional to its mass. Double the mass, double the radius. For Ton 618, the Schwarzschild radius works out to approximately 1,300 astronomical units. The diameter of the event horizon is therefore about 2,600 astronomical units. Let us put this in context. Mercury, the closest planet to the Sun, orbits at an average distance of about 0.39 astronomical units. Venus orbits at about 0.72. Earth, by definition, orbits at 1 astronomical unit. Mars orbits at about 1.52. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units. Saturn, famous for its rings, orbits at about 9.5. Uranus orbits at roughly 19.2. Neptune, the most distant planet, orbits at about 30 astronomical units, and Pluto, the dwarf planet, orbits at an average of roughly 39.5 astronomical units from the Sun. The event horizon of TON 618 extends to 1,300 astronomical units from the center. That means it extends more than 33 times farther from the center than Pluto orbits from the Sun. The entire known solar system, from the Sun to Pluto, could fit inside the event horizon of TON 618 more than 30 times over in terms of radius. You could line up more than 30 copies of our solar system, end to end, from the center of TON 618 to its event horizon. If you placed the Sun at the center of TON 618, Earth's orbit would be deep, inside the event horizon. Mars would be inside. Jupiter would be inside. Saturn would be inside. Uranus and Neptune would be inside. Pluto would be inside. You would have to travel more than 30 times farther than Pluto to reach the boundary of the event horizon. Everything within that boundary is, by definition, inside the black hole. Nothing that crosses that line can ever return. To help you visualize just how vast this is, imagine you could somehow travel at the speed of a commercial airplane, roughly 900 kilometers per hour. To fly from one side of TON 618's event horizon to the other, a distance of roughly 390 billion kilometers, it would take you approximately 49,500 years. That is longer than the entire span of recorded human civilization. You would have set off before the last ice age ended, before the first cities were built, before the invention of writing, before the domestication of animals, and you would still not have arrived. Or imagine driving a car at highway speed, about 100 kilometers per hour. The trip across the event horizon would take roughly 445,000 years. That is roughly the time that has elapsed since Homo sapiens first appeared on Earth. Our entire existence as a species would be consumed by a single drive across this black hole. Let us compare TON 618 to other well-known black holes. Sagittarius A star, the black hole at the center of the Milky Way, has a mass of 4 million solar masses and a Schwarzschild radius of about 0.08 astronomical units, or roughly 12 million kilometers. That is about 17 times the radius of the Sun. It is large, but it would fit comfortably inside the orbit of Mercury. M87 star, the first black hole ever imaged, has a mass of 6.5 billion solar masses and an event horizon radius of about 120 astronomical units. That is much larger, extending past the orbit of Pluto, but not enormously beyond it. TON 618's event horizon is roughly 10 times larger than M87 stars. It is in a different class entirely. There is another way to think about the size of TON 618's event horizon. Light, which travels at approximately 300,000 kilometers per second, takes about 8 minutes and 20 seconds to travel from the Sun to the Earth, a distance of 1 astronomical unit. To travel from one side of TON 618's event horizon to the other, a distance of 2,600 astronomical units, light would take roughly 15 days. 2 full weeks, at the fastest speed anything can travel in the universe, just to cross from one side of this object to the other. For comparison, light crosses our entire solar system, from the Sun to Pluto and back, in about 11 hours. TON 618's event horizon is roughly 33 times wider, but the event horizon is not the only remarkable feature of TON 618. Surrounding the CHI black hole is an accretion disk, a vast, swirling disk of gas, dust, and plasma spiraling inward toward the event horizon. The accretion disk is where the action happens. It is the engine that powers the quasar. As material in the disk spirals inward, it is compressed and heated by friction and gravitational forces. The innermost regions of the disk reach temperatures of millions, sometimes billions of degrees. At these temperatures, the gas emits enormous amounts of radiation across the entire electromagnetic spectrum, from radio waves to visible light to X-rays and gamma rays. This is the source of the quasar's incredible luminosity. The accretion disk of TON 618 is estimated to be many times larger than the event horizon itself. While the exact size is difficult to determine from our vantage point, 10.4 billion light-years away, theoretical models suggest it could extend hundreds or even thousands of astronomical units beyond the event horizon. The total luminous region, including both the accretion disk and the broader galactic environment affected by the quasar's output, is enormous. And then there is the nebula. TON 618 is surrounded by an enormous cloud of hot, glowing gas called a Lyman alpha nebula. Lyman alpha emission comes from hydrogen atoms that have been excited by ultraviolet radiation and are releasing that energy as they return to their ground state. The nebula surrounding TON 618 extends across roughly 100 kiloparsecs, which is about 326,000 light-years. For reference, the entire Milky Way galaxy is roughly 100,000 light-years in diameter. The glowing gas cloud around TON 618 is more than 3 times the diameter of our galaxy. This vast nebula is being illuminated and energized by the quasar's radiation, a cosmic lantern casting its light across a region of space so enormous that it dwarfs entire galaxies. Let us try one more comparison to help anchor these numbers. If you could somehow see TON 618's event horizon from a vantage point where it filled the same angular size as the full moon in Earth's sky, you would need to be roughly 83 light-years away. From that distance, the event horizon would appear as a dark circle, perfectly black, surrounded by the blazing accretion disk. The accretion disk would be blindingly bright, brighter than anything you have ever seen. And beyond it, stretching across a huge swath of sky, the Lyman Alpha Nebula would glow with a soft ethereal light, a cosmic halo hundreds of thousands of light-years across. It is worth pausing here to reflect on something. When we talk about the size and mass of TON 618, we are talking about a real object. This is not a thought experiment. This is not science fiction. This is something that actually exists, or more precisely, existed, 10.4 billion years ago, in a part of the universe so distant that the light we see from it has been traveling through the expanding cosmos, since before the Earth, the Sun, or even the Milky Way in its current form existed. The photons that our telescopes collect from TON 618 left their source when the universe was barely a quarter of its current age. They have been crossing the void of intergalactic space ever since, stretched and reddened by the expansion of the universe, finally arriving at our detectors after a journey of over 10 billion years. And during all those billions of years, TON 618 has continued to evolve. The quasar phase, the period of intense activity driven by rapid accretion, does not last forever. Eventually, the supply of gas feeding the black hole diminishes. The accretion disk thins out. The luminosity fades. The quasar turns off, and what remains is a massive but quiet black hole sitting at the center of a large galaxy. It is likely that the descendant of TON 618, whatever galaxy it lives in today, is a relatively normal-looking elliptical galaxy with an enormous but dormant black hole at its center. The fireworks are long over, but the black hole remains patient and eternal, a gravitational scar on the fabric of space-time. Now, let us turn our attention to the extraordinary physics of what happens in the immediate vicinity of this monster. Because the region around TON 618 is one of the most extreme environments in the universe, a place where the laws of physics are pushed to their absolute limits. Section 4. The Engine of Destruction. To understand what happens near TON 618, we need to understand how matter behaves in the presence of extreme gravity. And the first thing to understand is that matter does not simply fall straight into a black hole. If it did, there would be no quasar, no accretion disk, no spectacular light show visible across 10 billion light-years. The reason we can see TON 618 at all is precisely because matter does not fall straight in. It spirals. Imagine a cloud of gas drifting through the galaxy housing TON 618. The gas is pulled toward the black hole by gravity, but it also has its own motion, its own velocity, its own angular momentum. Angular momentum is a measure of rotational motion, and like energy, it is conserved. It cannot be created or destroyed, only transferred. A cloud of gas falling toward a black hole almost always has some angular momentum, because it is almost impossible for something to approach from a direction perfectly aligned with the center. Any slight offset, any tiny sideways velocity, gives the gas angular momentum. And because angular momentum must be conserved, the gas cannot fall straight in. Instead, it begins to orbit. As more and more gas is pulled toward the black hole, it collects into a disk. This is the accretion disk. The gas in the disk orbits the black hole at tremendous speeds, with the inner regions orbiting faster than the outer regions. This difference in speed creates friction between adjacent layers of gas. The friction heats the gas and causes it to slowly lose energy and angular momentum, spiraling gradually inward, closer and closer to the event horizon. The process is slow compared to the speed of the orbiting gas, but over time, material works its way from the outer edges of the disk to the inner edge, where it eventually crosses the event horizon and is swallowed by the black hole. The temperatures in the accretion disk increase dramatically as you move closer to the center. The outer parts of the disk might be at temperatures of thousands of degrees, similar to the surface of a star. But the inner parts, where the gas is compressed by enormous gravitational forces and heated by intense friction, can reach temperatures of millions or even billions of degrees. At these temperatures, the gas is not really gas anymore. It is plasma, a state of matter in which atoms are stripped of their electrons, leaving a seething soup of free electrons and bare atomic nuclei. This superheated plasma radiates energy across the electromagnetic spectrum. The cooler outer parts of the disk radiate mainly in the infrared and visible wavelengths. The hotter inner parts radiate in the ultraviolet and X-ray wavelengths. The very hottest regions, closest to the event horizon, can produce gamma rays. The total energy output from TON 618's accretion disk is staggering. As we mentioned earlier, its luminosity is roughly 140 trillion times that of the Sun. This makes it not just one of the brightest quasars, but one of the brightest persistent objects in the entire observable universe. To put this in perspective, the total luminosity of the Milky Way galaxy, including all of its stars, is roughly equivalent to about 30 billion solar luminosities. TON 618's quasar outshines the entire Milky Way by a factor of roughly 4,700. It is like comparing a candle to a searchlight. But where does all this energy come from? The answer is gravity. Specifically, it comes from the conversion of gravitational potential energy into radiation, as matter falls deeper into the gravitational well of the black hole. This is an extraordinarily efficient process. Nuclear fusion, the process that powers stars, converts roughly 0.7% of the rest mass energy of hydrogen into radiated energy. That is, for every kilogram of hydrogen fused, about 7 grams worth of energy is released, according to Einstein's famous equation, E equals mc squared. This is already vastly more efficient than chemical energy. The chemical combustion of gasoline, for example, converts only about 1/10 billionth of the fuel's rest mass into energy. Nuclear fusion is millions of times more efficient than chemistry. But gravitational accretion onto a black hole is even more efficient than nuclear fusion. For a non-rotating black hole, the maximum efficiency of energy extraction from accreting matter is about 5.7%. This means that for every kilogram of matter that spirals into the black hole, about 57 grams worth of mass energy is radiated away. That is roughly 8 times more efficient than nuclear fusion. But most real black holes are not stationary. They spin. And for a rapidly spinning black hole, also known as a Kerr black hole, the efficiency can be much higher. A maximally spinning black hole can convert up to about 42% of the rest mass of infalling matter into radiated energy. This is an almost absurdly efficient process. Nearly half of the matter's total mass energy is radiated away before it crosses the event horizon. This is why quasars are so luminous. They are converting matter into energy at an efficiency that makes nuclear fusion look wasteful. We do not know the exact spin rate of TON 618's black hole, but given the enormous luminosity of the quasar, it is reasonable to assume that it is spinning rapidly. A faster spin means a deeper gravitational well, which means higher temperatures in the inner accretion disk, which means more energy output. The spin also affects the size of the innermost stable circular orbit, the closest distance at which matter can orbit without inevitably falling in. For a non-spinning black hole, this distance is 3 Schwarzschild radii. For a maximally spinning black hole, it shrinks down to very close to the event horizon itself. The smaller the innermost stable orbit, the deeper into the gravitational well the gas can spiral before it crosses the point of no return, and the more energy it releases in the process. Now, let us talk about what happens to matter as it approaches the event horizon of TON 618. This is where the physics becomes truly extreme. First, there is the tidal force. In Newtonian physics, we often think of gravity as a single force pulling an object toward a massive body. But in reality, gravity varies with distance. The side of an object closer to the source of gravity feels a stronger pull than the side farther away. This difference in gravitational force across the extent of an object is called the tidal force. Near an ordinary star, tidal forces are negligible for anything smaller than a moon or planet. But near a black hole, they can become enormous. For stellar mass black holes, the tidal forces at the event horizon are extreme. An astronaut falling feet first into a stellar mass black hole would be stretched vertically and compressed horizontally, a process colorfully known as spaghettification. They would be torn apart long before reaching the event horizon. But here is something counterintuitive. For supermassive and ultramassive black holes like TON 618, the tidal forces at the event horizon are actually much weaker than for stellar mass black holes. This is because the event horizon is so much farther from the singularity. The tidal force at the event horizon scales inversely with the square of the black hole's mass. A more massive black hole has a larger event horizon, and the gravitational gradient across a human-sized object at that horizon is gentler. For TON 618, the tidal forces at the event horizon would be so mild that a hypothetical astronaut crossing it would feel essentially nothing unusual. There would be no stretching, no compression, no dramatic physical sensation. They would simply pass through an invisible boundary and never be able to return. The spaghettification would come later, much later, as they fell deeper into the interior and the tidal forces grew without limit as they approached the singularity. This is one of the most haunting aspects of ultramassive black holes. The event horizon is not a place of violence or drama. It is a quiet threshold. You cross it without fanfare, without pain, without any immediate indication that anything has changed. And yet everything has changed. You are now inside the black hole. The singularity is no longer something you might fall into. It is something you will fall into. In the geometry of space-time inside the event horizon, the singularity is not a place in space. It is a moment in time. It lies in your future, as surely and inevitably as tomorrow. No amount of acceleration, no matter how powerful your rockets, can prevent you from reaching it. You are trapped not by walls or barriers, but by the geometry of space-time itself. Second, there is the phenomenon of time dilation. According to general relativity, time passes more slowly in stronger gravitational fields. This effect has been measured and confirmed to extraordinary precision using atomic clocks at different altitudes on Earth. The closer you are to a massive object, the slower your clock ticks compared to a clock far away. Near the event horizon of a black hole, this effect becomes extreme. To an observer watching from a safe distance, an object falling toward the event horizon would appear to slow down as it approached. Its light would become increasingly redshifted, stretching to longer and longer wavelengths. The object would appear to fade, growing dimmer and redder, asymptotically approaching the event horizon, but never quite reaching it from the distant observer's perspective. In reality, the infalling object crosses the event horizon in finite time according to its own clock. But from the outside, it appears to freeze at the boundary, its image lingering as an ever fainter ghost. Third, there is the bending of light. The intense gravity near a black hole curves space-time so severely that light itself follows curved paths. Photons that pass close to the event horizon can be deflected by large angles, or even captured entirely. At a specific distance from the center, called the photon sphere, light can theoretically orbit the black hole in a circular path. For TON 618, the photon sphere lies at about 1.5 Schwarzschild radii from the center. If you could hover at the photon sphere of TON 618 and look forward, you would see the back of your own head, because light would wrap all the way around the black hole and return to you. In practice, this orbit is unstable, and any slight perturbation would send the photon either spiraling into the black hole or escaping to infinity. But it illustrates the profound distortion of space-time in the vicinity of these objects. The bending of light also creates the visual appearance of a black hole as seen from the outside. If you could observe TON 618 from a safe distance, the black hole itself would appear as a perfectly circular dark region, the shadow, surrounded by a bright ring of light. This ring is formed by photons that pass close to the event horizon and are bent around the black hole before escaping toward your eyes. The shadow would be slightly larger than the event horizon itself, about 2.6 times the Schwarzschild radius for a non-spinning black hole. For TON 618, this shadow would span roughly 3,400 astronomical units across. Behind and around the shadow, the accretion disk would blaze with incredible brightness, its light warped and magnified by gravitational lensing into arcs and rings that defy ordinary geometry. Fourth, there are the relativistic jets. Many quasars, including some of the most powerful ones, produce narrow beams of material launched from the vicinity of the black hole at speeds approaching the speed of light. These are called relativistic jets, and they are among the most energetic phenomena in the universe. The jets are thought to be powered by the rotational energy of the spinning black hole, extracted through a mechanism proposed by Roger Blandford and Roman Zanajek in 1977. In this mechanism, magnetic field lines threading the spinning black hole's event horizon are twisted by the rotation of spacetime itself, launching material outward along the rotational axis at tremendous speeds. Relativistic jets can extend for thousands or even millions of light years beyond the host galaxy, plowing through the intergalactic medium and creating enormous lobes of radio-emitting plasma. They carry tremendous amounts of energy and can have a profound impact on their surroundings, heating the intergalactic gas, suppressing star formation in neighboring galaxies, and redistributing energy across vast scales. Whether TON 618 produces prominent jets is not entirely clear from current observations, but given its extreme mass and luminosity, it is highly likely that it did at various points during its active quasar phase. The accretion process is not steady and continuous. It is variable, chaotic, and sometimes violent. The flow of gas into the accretion disk is influenced by the complex gravitational dynamics of the surrounding galaxy, including interactions with nearby stars, gas clouds, and even other black holes. The disk itself is subject to instabilities that can cause sudden increases in the accretion rate, producing flares and outbursts of dramatically increased luminosity. These variations can occur on timescales ranging from hours to years, providing valuable clues about the size and structure of the emitting region. There is also the phenomenon of tidal disruption events, which occur when a star passes too close to the black hole and is torn apart by tidal forces. The stellar material is stretched into a long stream that wraps around the black hole, forming a temporary accretion disk and producing a bright flare that can last for months or years. 4. A black hole as massive as TON 618, the tidal disruption radius, the distance at which a star would be torn apart, is actually inside the event horizon for most types of stars. This means that TON 618 would swallow most stars whole without disrupting them first. The star would simply pass through the event horizon intact and disappear. Only the most extended, least dense stars, such as red giants, would be disrupted outside the event horizon. Think about that for a moment. A star like our Sun, 1.4 million kilometers in diameter, containing 330,000 Earth masses of material, would fall into Ton 618 without even being torn apart. It would simply vanish, as if it had never existed. The black hole would barely notice. Its mass would increase by 1 solar mass out of 66 billion, a change of about 1 part in 66 billion. The Sun would make no discernible difference whatsoever to this cosmic monster. Let us dwell on one more aspect of the accretion process, because it reveals something profound about the nature of energy in the universe. The total amount of energy released by the accretion disk of Ton 618 over its active quasar lifetime is almost incomprehensible. If the black hole grew from, say, 1 billion solar masses to 66 billion solar masses through accretion, and if roughly 10% of the rest mass energy of the accreted material was radiated away, then the total energy output over the quasar's lifetime would be on the order of 10 to the 55th joules. For comparison, the total energy output of our Sun over its entire 10 billion year lifetime is about 1.2 times 10 to the 44th joules. Ton 618's quasar output exceeds the Sun's total lifetime energy by a factor of roughly 100 billion. One single quasar, powered by one single black hole, released more energy than 100 billion suns will produce in their entire lives. That energy-heated gas drove outflows, shaped galaxies, and influenced the evolution of the cosmos across hundreds of thousands of light years. It is hard to overstate the significance of this. In a universe governed by the flow and transformation of energy, TON 618 was one of the greatest energy engines ever assembled by nature. There is also the question of what the accretion disk actually looks like, which is far stranger than most people imagine. Because of the extreme curvature of space-time near the black hole, the appearance of the accretion disk is dramatically distorted. If you could observe the disk from above, it would look roughly like a flat ring surrounding the black shadow of the event horizon. But if you observed it from an angle, the distortion would be remarkable. The far side of the disk, the part behind the black hole from your perspective, would appear to bend upward, curving above and below the shadow. This is because light from the far side of the disk is bent around the black hole by gravity, allowing you to see parts of the disk that should be hidden behind the event horizon. You would see the top of the disk above the shadow and the bottom of the disk below it, all at the same time. The image would be smeared and brightened by gravitational lensing, with one side of the disk appearing noticeably brighter than the other due to relativistic beaming. The Doppler effect applied to material moving at a significant fraction of the speed of light. The approaching side of the disk, where material is moving toward you, would be blue-shifted and brightened. The receding side, where material is moving away from you, would be red-shifted and dimmed. The overall effect is a hauntingly beautiful, asymmetric ring of light surrounding a perfectly circular void of absolute darkness. This is, in fact, very close to what the Event Horizon Telescope captured when it imaged M87 star in 2019. That image, the first ever taken of a black hole, shows exactly this pattern. A bright, asymmetric ring surrounding a dark central shadow. For Ton 618, the pattern would be similar, but the scale would be vastly larger. This is the engine at the heart of Ton 618, a gravitational vortex of almost inconceivable power, converting the mass of stars and gas clouds into radiant energy with an efficiency that exceeds nuclear fusion, blazing across the cosmos with the light of 140 trillion suns, warping space-time across a region larger than our solar system, and swallowing stars whole as casually as a whale swallows plankton. It is destruction on a scale that the human mind was never designed to comprehend. And yet, as we will see in the next part of our journey, this destruction is not random. It is not purposeless. It is intimately connected to the structure and evolution of the universe itself. Section 5. Architects of the Cosmos. We have now seen the engine of TON 618 up close, explored its accretion disk, its tidal forces, its time dilation, its bending of light, and its relativistic jets. We have seen how matter spirals inward, heated to billions of degrees, radiating energy with an efficiency that exceeds nuclear fusion. We have seen how even entire stars can be swallowed whole by this gravitational monster, vanishing without a trace behind the event horizon. But the story of TON 618 is not just a story of destruction. It is also, surprisingly, a story of creation. Because the energy released by quasars like TON 618 does not simply dissipate harmlessly into the void. It interacts with its surroundings in profound ways, shaping the galaxies and the cosmic structures around it. In this section, we will explore how supermassive black holes, far from being mere consumers, are actually among the most important architects of the universe we live in. For a long time, supermassive black holes were thought of as cosmic oddities. Interesting, certainly. Spectacular, absolutely. But essentially irrelevant to the broader story of the universe. They sat at the centers of galaxies, occasionally flaring up as quasars, but their influence was thought to be limited to the relatively small region immediately around them. The rest of the galaxy, the hundreds of billions of stars spread across 100,000 light-years, went about its business unaffected. This view began to change in the late 1990s and early 2000s, with a series of discoveries that revealed a deep and unexpected connection between supermassive black holes and the galaxies that host them. The first clue came from a remarkable correlation between the mass of the central black hole and a property of the galaxy called the velocity dispersion of the bulge. Let us unpack that. Most large galaxies have a central bulge, a dense, roughly spherical concentration of stars at the center. The velocity dispersion is a measure of how fast the stars in the bulge are moving relative to each other. A higher velocity dispersion means the stars are moving faster, which in turn means the bulge is more massive, because it takes a deeper gravitational well to keep those fast-moving stars bound. What astronomers discovered was that the mass of the central black hole is very tightly correlated with the velocity dispersion of the bulge. Galaxies with more massive bulges have more massive black holes, and the relationship follows a precise mathematical formula. This correlation is now known as the M-sigma relation, and it has been confirmed across dozens of galaxies spanning a wide range of masses. The M-sigma relation is remarkable because the black hole and the bulge are vastly different in size. The black hole occupies a tiny volume at the very center of the galaxy. The bulge extends across thousands of light-years. The black hole contains only a small fraction of the total mass of the bulge, typically about 0.1 to 0.5%. And yet the two are precisely correlated. It is as if the black hole and the galaxy know about each other, as if they have co-evolved, each influencing the growth of the other through some mechanism that connects scales differing by factors of millions. That mechanism is feedback, Specifically, it is the energy output of the active galactic nucleus, the quasar phase of the black hole's life, that regulates the growth of the galaxy around it. Here is how it works. When the black hole is actively accreting material and shining as a quasar, it releases enormous amounts of energy into its surroundings. This energy heats the surrounding gas, making it harder for that gas to collapse and form new stars. In extreme cases, the quasar's energy can drive powerful outflows, winds of superheated gas traveling at thousands of kilometers per second, that blow material out of the galaxy entirely. This removes the raw material needed for star formation, effectively shutting down the galaxy's ability to grow. This process is called quasar feedback, or more broadly, active galactic nucleus feedback, and it is now considered one of the most important processes in the evolution of galaxies. Without feedback from supermassive black holes, computer simulations predict that galaxies should be much more massive than they actually are. They should contain far more stars and far more gas. The fact that real galaxies are smaller and less massive than these predictions suggests that something is removing gas and suppressing star formation. That something, in many cases, is the black hole. Think about the irony of this for a moment. A black hole, an object defined by its ability to consume, is actually one of the most powerful mechanisms in the universe for preventing consumption. By eating a small amount of material and converting it into energy and outflows, the black hole prevents a much larger amount of material from ever being consumed. It is a cosmic thermostat, regulating the temperature and density of the surrounding gas, maintaining a balance between growth and starvation that shapes the final mass and structure of the galaxy. TON 618, at 66 billion solar masses, and with a luminosity of 140 trillion solar luminosities, represents this process taken to an extreme. The energy output from its quasar phase would have had a profound impact on its host galaxy and the surrounding intergalactic medium. The powerful radiation and potential outflows would have heated gas across hundreds of thousands of light years, suppressing star formation not just in its own galaxy but potentially in neighboring galaxies as well. The Lyman Alpha Nebula surrounding TON 618, stretching across 326,000 light-years, is direct evidence of this process. The nebula is being illuminated and energized by the quasar's radiation, a visible sign of the vast reach of the black hole's influence. This is one of the great revelations of modern astrophysics. Supermassive black holes are not passive inhabitants of galaxies. They are active participants in the life cycle of the cosmos. They shape the galaxies they live in, influence the galaxies around them, and play a crucial role in determining the large-scale structure of the universe. Without supermassive black holes and their feedback, the universe would look very different. Galaxies would be more massive, more gas-rich, and more actively forming stars. The balance of elements in the intergalactic medium would be different. The distribution of matter on the largest scales would be altered. In a very real sense, supermassive black holes are architects. They build by destroying. They create order by unleashing chaos. They shape the cosmos not by adding material but by removing it, heating it, and redistributing it across vast distances. And TON 618, as one of the most massive and most luminous examples of this phenomenon ever observed, represents one of the most powerful architects in the history of the universe. Let us now zoom out even further and consider the broader cosmic context in which TON 618 exists. The universe, on the largest scales, is not a random scattering of galaxies. It has structure. Galaxies are not distributed uniformly through space. Instead, they are arranged in a vast three-dimensional network of filaments and walls surrounding enormous, nearly empty voids. This network is called the cosmic web, and it is the largest known structure in the universe. The filaments of the cosmic web can stretch for hundreds of millions of light years, containing thousands of galaxies strung along them like pearls on a string. At the intersections of filaments, where multiple threads of the web converge, sit the densest concentrations of matter. Galaxy clusters, enormous collections of hundreds or thousands of galaxies bound together by gravity, embedded in vast halos of dark matter and bathed in hot, X-ray emitting gas. The cosmic web is a product of gravity acting on the tiny density fluctuations that existed in the very early universe, just a few 100,000 years after the Big Bang. These fluctuations, which we can see imprinted in the cosmic microwave background radiation, the afterglow of the Big Bang, were incredibly small, variations of only about 1 part in 100,000. But over billions of years, gravity amplified them. Regions that were slightly denser than average pulled in more matter, growing denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming emptier. Over time, the cosmic web emerged, a vast scaffolding of dark matter along which ordinary matter, gas, and eventually galaxies accumulated. Supermassive black holes and their quasar feedback play a role in shaping the cosmic web. The energy injected into the intergalactic medium by quasars helps to regulate the temperature and density of the gas within and around the filaments and clusters of the web. Without this energy input, gas would cool more efficiently, collapse more readily, and form more galaxies and more stars than we actually observe. The feedback from quasars acts as a heating mechanism that keeps the gas in the cosmic web warm enough to resist collapse, maintaining the delicate balance between structure formation and dispersal that gives the universe its observed properties. TON 618, shining at a redshift of 2.2, was active during a period of cosmic history known as the epoch of peak quasar activity. This was the time, roughly 2 to 3 billion years after the Big Bang, when the supermassive black holes at the centers of galaxies were growing most rapidly and quasars were most common. The universe was denser and more gas-rich than it is today, providing abundant fuel for the black holes. Galaxy mergers were more frequent, funneling gas toward the central black holes and triggering episodes of intense accretion. It was a tumultuous, energetic era, and TON 618 was one of its most extreme products. Since that time, roughly 10 billion years ago, the universe has continued to expand and evolve. The density of gas available for accretion has decreased. Galaxy mergers have become less frequent. Most supermassive black holes have settled into a quiet dormancy, their quasar phases long since ended. The modern universe is a calmer, more sedate place than the cosmos of 10 billion years ago. But the black holes remain. Every large galaxy still harbors one at its center. They are sleeping, not dead. And occasionally, even in the present-day universe, a galaxy merger or a close encounter with a dense cloud of gas can reignite a dormant black hole, producing a brief flare of activity that echoes the glory days of the quasar epoch. Let us now consider one more aspect of supermassive black holes that connects them to the very fabric of space and time: gravitational waves. When two supermassive black holes merge, which happens when their host galaxies collide, the merger produces gravitational waves at very low frequencies. These waves are too low in frequency for current ground-based detectors like LIGO and Virgo to detect, but they may be detectable by future space-based observatories like LISA, the Laser Interferometer Space Antenna, or through a technique called pulsar timing arrays. Pulsar timing arrays use the incredibly regular pulses from millisecond pulsars, rapidly spinning neutron stars, as a kind of cosmic timing network. Gravitational waves passing through the space between the pulsars and the Earth cause tiny correlated changes in the arrival times of the pulses. By monitoring dozens of pulsars across the sky, astronomers can search for the distinctive pattern of timing variations produced by a background of gravitational waves from merging supermassive black holes throughout the universe. In 2023, several pulsar timing array collaborations announced evidence for just such a gravitational wave background. A persistent hum of space-time vibrations produced by the cumulative effect of countless supermassive black hole mergers throughout cosmic history. This was one of the most important discoveries in recent astrophysics, providing direct evidence that supermassive black holes regularly merge and confirming a key prediction of general relativity. The gravitational waves from the merger of two black holes as massive as TON 618 would be extraordinarily powerful. They would ripple across the universe, stretching and compressing space itself as they passed. They would carry information about the masses, spins, and orbital dynamics of the merging black holes, providing insights into the physics of gravity in its most extreme regime. Future detections of such events will open a new window on the universe, allowing us to study the most massive objects in existence in a way that electromagnetic observations alone cannot achieve. This is the broader story of TON 618. It is not just a big black hole, it is a product of billions of years of cosmic evolution, shaped by the interplay of gravity, gas dynamics, galaxy mergers, and the complex feedback processes that connect black holes to their host galaxies. It is an architect of cosmic structure, an engine of galactic regulation, and a source of gravitational waves that ripple across the fabric of space-time. It represents one extreme of a population of objects that plays a central role in the life of the universe. And yet, for all its power and all its influence, it is subject to the same laws of physics as everything else. Even TON 618 is not eternal. And, in the final part of our journey, we will look into the deep future and ask what ultimately becomes of a black hole this massive, on timescales so vast that they make the current age of the universe seem like the blink of an eye. Section 6. The Deep Future. We have traveled through the formation of TON 618, explored its staggering scale, examined the physics of its accretion disk, and seen how it shapes the cosmos around it. Now, in this final section, we turn our gaze forward into the deep future. We ask a question that pushes the limits of physics and philosophy alike. What happens to a black hole this massive when the universe grows old? When the stars have all burned out, when the galaxies have dissolved, when the cosmos itself approaches its final state, what becomes of TON 618? The answer is one of the most profound and haunting stories in all of science. It begins with the discovery made by a physicist in a wheelchair, and it ends at the very edge of what the human mind can imagine. Everything in the universe has a beginning, a middle, and an end. Stars are born, they shine for millions or billions of years, and they die. Galaxies assemble, evolve, and eventually fade. Even the universe itself had, a beginning 13.8 billion years ago, and it will, in some sense, have an end. The question is, what happens to black holes? What is the fate of an object like TON 618, a gravitational abyss containing 66 billion solar masses on timescales stretching far into the future? For a long time, black holes were thought to be truly eternal. Once formed, they could only grow. Matter falls in, the black hole gets bigger. Nothing comes out. The event horizon is a one-way boundary. The second law of thermodynamics seems to suggest that the entropy of the universe can only increase. And black holes, by hiding information behind their event horizons, seem to provide an infinite entropy sink. In this picture, black holes would be the last objects standing at the end of time, the ultimate survivors of a dying universe. Then, in 1974, Stephen Hawking changed everything. Hawking, building on earlier work by Jacob Bekenstein and drawing on insights from quantum field theory, showed that black holes are not perfectly black. They emit a faint but real form of radiation, now called Hawking radiation, that causes them to slowly lose mass and energy over time. This was one of the most stunning theoretical discoveries of the 20th century, a bridge between general relativity, quantum mechanics, and thermodynamics that revealed deep truths about the nature of space-time. The mechanism of Hawking radiation is subtle and counterintuitive. In quantum mechanics, empty space is not truly empty. The vacuum is a seething froth of virtual particle-antiparticle pairs, constantly popping into existence and annihilating each other in times too short to measure directly. Normally, these virtual pairs have no observable effect. But near the event horizon of a black hole, something strange happens. A virtual pair can be created right at the boundary, with one particle falling into the black hole and the other escaping to infinity. The escaping particle becomes real, carrying away a small amount of energy. From the perspective of the distant observer, the black hole has emitted a particle. Over time, these emitted particles carry away mass and energy from the black hole, causing it to shrink. The temperature of the Hawking radiation is inversely proportional to the mass of the black hole. More massive black holes are colder. Less massive black holes are hotter. For a stellar mass black hole of about 10 solar masses, the Hawking temperature is roughly 6 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation, which has a temperature of about 2.7 degrees above absolute zero. This means that stellar mass black holes in the current universe are actually absorbing more energy from the cosmic microwave background than they are emitting through Hawking radiation. They are growing, not shrinking. The same is true, even more dramatically, for supermassive and ultramassive black holes like TON 618. The Hawking temperature of TON 618 is so infinitesimally small, so incomprehensibly close to absolute zero, that it is essentially meaningless in the current universe. The rate of mass loss through Hawking radiation is negligibly small compared to the rate of mass gain through accretion, even the trickle of matter that falls into a dormant black hole. But the universe will not always be as it is today. The cosmic microwave background is cooling as the universe expands. Its temperature decreases inversely with the scale factor of the universe. In the far future, as the expansion continues and accelerates, the background radiation will cool to temperatures far below the Hawking temperature of even the most massive black holes. At that point, black holes will be losing more energy through Hawking radiation than they gain from their environment. they will begin to evaporate. The timescale for this evaporation is almost beyond imagination. The time it takes for a black hole to evaporate through Hawking radiation scales as the cube of its mass. A stellar mass black hole of 10 solar masses would take roughly 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros. For comparison, the current age of the universe is about 1.4 times 10 to the 10th years, or 14 billion years. 10 to the 67th years is so much longer than the current age of the universe that no analogy can bridge the gap. If the current age of the universe were a single second, the evaporation time of a stellar mass black hole would be roughly 3 times 10 to the 49th years. The ratio is incomprehensible. For TON 618, at 66 billion solar masses, the evaporation time is even more extreme. Scaling as the cube of the mass, TON 618 would take roughly 10 to the power of 106 years to evaporate. That is a 1 followed by 106 zeros. This number is so large that it defies any attempt at visualization. It is longer than the time it would take for every star in the universe to burn out. It is longer than the time it would take for all remaining matter to decay. It is longer than almost any process in physics, with the possible exception of certain hypothetical proton decay timescales and the evaporation times of even more massive hypothetical objects. Let us try to place this in the context of the long-term future of the universe, as best we understand it. The stelliferous era, the age of stars, began roughly a few 100 million years after the Big Bang with the formation of the first stars, and will continue for perhaps another 100 trillion years, roughly 10 to the 14th years. During this time, stars will continue to form, shine, and die. But the rate of star formation is already declining. The universe is running out of the raw materials needed to make new stars. The gas in galaxies is being used up, blown out by stellar winds and supernovae, or heated by black hole feedback until it can no longer collapse. Eventually, the last stars will flicker out, and the universe will enter a long, dark era with no new sources of light. After the last stars die, the universe will be populated by the remnants, white dwarfs, neutron stars, and black holes, along with a diffuse background of cold gas, dark matter, and radiation. The white dwarfs will slowly cool over trillions of years, fading from white to yellow to red, to infrared to invisible, eventually becoming black dwarfs, objects too cold to emit any detectable radiation. This process takes roughly 10 to the 15th to 10 to the 25th years, depending on the mass of the white dwarf. Gravitational interactions between objects in galaxies will gradually rearrange their orbits. Most stars and stellar remnants will be ejected from their galaxies through close gravitational encounters, flung out into intergalactic space. A small fraction will lose energy through these encounters and spiral inward, eventually falling into the central black hole. Over time scales of roughly 10 to the 19th to 10 to the 20th years, galaxies as we know them will dissolve, leaving behind their central black holes surrounded by a sparse halo of ejected remnants. Over even longer time scales, the protons and neutrons that make up ordinary matter may themselves be unstable. Some theories of particle physics predict that protons will eventually decay into lighter particles, with a half-life of roughly 10 to the 36th to 10 to the 41st years, depending on the theory. If proton decay occurs, all ordinary matter will eventually disintegrate. Atoms will fall apart. White dwarfs and neutron stars will dissolve. The only macroscopic objects remaining will be black holes. There is a haunting beauty to this vision of the far future. A universe in which the only surviving macroscopic objects are black holes, each one a sealed vault of gravitational memory, containing within their event horizons the accumulated history of countless stars and galaxies and civilizations that may have risen and fallen long before. Everything that ever existed, every atom of every star, every photon of every sunset, every thought of every being that ever lived, all of it either scattered as radiation into the void or locked behind the event horizons of black holes. The universe becomes a graveyard, but a patient one, because even the tombstones will eventually dissolve. This brings us to the black hole era, the period from roughly 10 to the 40th to 10 to the 100th years, and beyond. During this era, black holes are the dominant objects in the universe. They sit in the darkness, slowly evaporating through Hawking radiation, their event horizons shrinking imperceptibly over timescales that dwarf everything that came before. The universe is cold, dark, and nearly empty. The only light comes from the faint glow of Hawking radiation. The last whisper of the dying black holes. Stellar mass black holes evaporate first, in roughly 10 to the 67th years. Supermassive black holes last longer. And the most massive black holes of all, the ultramassive monsters like TON 618, persist the longest, their immense mass buying them time on a scale that is almost literally unimaginable. But eventually, even TON 618 will evaporate. After roughly 10 to the 106th years, its mass will have been entirely converted into Hawking radiation, a faint shower of photons, neutrinos, and other particles dispersing into the ever-expanding void. The event horizon will shrink to nothing. The singularity, if it truly exists as predicted by classical general relativity, will be exposed, or perhaps resolved by whatever quantum theory of gravity ultimately replaces our current understanding. And with the evaporation of the last black hole, the universe will enter its final state, a cold, dark, infinitely expanding void, populated by nothing but a thin, cooling gas of photons, neutrinos, electrons, and positrons, all moving ever farther apart, approaching but never quite reaching absolute zero. This is the heat death of the universe, the state of maximum entropy from which no further work can be extracted, no further structure can form, and no further change of any meaningful kind can occur. It is the ultimate end state predicted by our current understanding of thermodynamics and cosmology. And it is the fate that awaits everything in the universe, from the smallest atom to the largest black hole. But there is a strange kind of beauty in this picture, if you are willing to look for it. The fact that an object like TON 618, so massive and so powerful that it outshines entire galaxies and warps space-time across solar system-sized regions, is itself temporary, is itself subject to the same laws that govern everything else, speaks to a deep unity in the physics of the universe. There is no special exemption for the most extreme objects. The same quantum mechanics that governs the behavior of electrons in atoms also governs the evaporation of black holes. The same thermodynamics that determines which way heat flows in your kitchen also determines the ultimate fate of the cosmos. The universe does not play favorites. It applies its rules uniformly, to the very small and the very large, to the very brief and the very long-lived. And perhaps there is comfort in the scale of things, too. We spend our lives worrying about deadlines and appointments, about minutes and hours and years. We measure our time in decades, at most a century. And here's an object that will persist for 10 to the 106th years, a span of time so vast that the entire history of human civilization, the entire history of life on Earth, the entire history of the Earth itself, the entire history of the Sun, the entire history of the Milky Way, all of it together, is less than a rounding error, the time scale of Ton. 618's eventual evaporation, everything that has ever happened in the universe so far, is essentially simultaneous. It all occurred in the first instant. There is one final thought worth considering before we draw this journey to a close. In the very last moments of a black hole's life, as its mass dwindles to almost nothing, the temperature of its Hawking radiation rises dramatically. In its final seconds, the black hole becomes incredibly hot, releasing a burst of high-energy radiation in a final flash. The details of this final explosion are still debated by physicists, because it occurs in a regime where both quantum mechanics and general relativity are important, and we do not yet have a fully consistent theory that combines the two. But whatever happens in those final moments, the result is the same. The black hole is gone. All that remains is radiation, dispersing into the void. And the question of what happened to all the information that fell into the black hole over its lifetime. The information about every star, every planet, every atom that crossed the event horizon is one of the deepest unsolved problems in theoretical physics. It is called the black hole information paradox, and it has occupied some of the greatest minds in physics for nearly 50 years. Stephen Hawking initially believed that the information was destroyed, which would violate the fundamental principles of quantum mechanics. He later revised his position, suggesting that the information might be preserved in some form, perhaps encoded in the Hawking radiation itself through subtle correlations too complex to easily detect. The debate continues today, and its resolution will almost certainly require a new understanding of the relationship between gravity and quantum mechanics, an understanding that may reshape our view of space-time itself. Let us return, for a moment, to where we began. A faint point of light in the constellation Cons Venatici, catalogued in 1957 by astronomers who had no idea what they were looking at. A number in a table, TON 618, that would have been forgotten if not for the stubborn curiosity of scientists who kept asking what it was, kept measuring, kept calculating, kept pushing the limits of their instruments and their theories. What they found was one of the most extraordinary objects in the observable universe. A black hole 66 billion times the mass of the Sun, powering a quasar 140 trillion times more luminous than the Sun, surrounded by a glowing nebula 3 times the diameter of the Milky Way, warping space-time across a region 30 times wider than our solar system. An object that formed in the young universe, grew through billions of years of accretion and mergers, shaped the galaxy around it through powerful feedback, and now sits in the distant cosmos as a relic of a more violent, more energetic era. We cannot visit it. We cannot even see it as it is today. We can only see it as it was 10.4 billion years ago, a snapshot of a moment in its long history. By now, the quasar has almost certainly turned off. The accretion disk has faded. The black hole sits in darkness, quietly digesting its accumulated mass, waiting for the slow, patient process of Hawking evaporation to gradually, over timescales beyond human imagination, return its substance to the universe from which it came. There is something profoundly humbling about contemplating objects like TON 618. They remind us of our place in the cosmos, which is simultaneously insignificant and extraordinary. Insignificant because we are tiny, brief, fragile creatures living on a small rocky planet orbiting an ordinary star in an ordinary galaxy, one among hundreds of billions of galaxies in the observable universe. Extraordinary because we are the creatures who figured all of this out. We are the ones who looked at a faint point of light and deduced that it was powered by a black hole, 66 billion times more massive than the Sun. We are the ones who wrote down the equations of general relativity and quantum mechanics and used them to predict the existence and properties of objects we will never touch, never visit, never experience directly. We are the universe looking at itself, and what we see is magnificent beyond words. Tonight, as you lie here in the darkness, consider that the darkness around you is not so different from the darkness inside the event horizon of TON 618. It is quiet. It is still. It is vast. But it is not empty. It is filled with the same physical laws, the same fundamental forces, the same quantum fields that govern everything in the cosmos. The atoms in your body were forged in stars that lived and died billions of years ago. The iron in your blood was created in a supernova. The calcium in your bones was scattered into space by an exploding star and reassembled by gravity into a new solar system, a new planet, and, eventually, you. You are made of the same stuff as TON 618. You are subject to the same gravity. You are governed by the same equations. The difference is one of scale, not of kind. And so, as the numbers grow large and the distances grow vast and the timescales stretch beyond imagination, let yourself drift. Let the enormity of the cosmos be not a source of anxiety, but of peace. You do not need to comprehend every number. You do not need to visualize every distance. You do not need to hold it all in your mind at once. Just know that it is there, that the universe is vast and strange and beautiful and governed by laws of breathtaking elegance. That somewhere, 10.4 billion light years from where you are lying right now, there is a black hole so massive that it could swallow our entire solar system without noticing. And that you, improbably, impossibly, beautifully, are here to know about it. The stars outside your window, if you can see them, are pinpoints of nuclear fire, each one a furnace of hydrogen and helium burning with the patient intensity that has illuminated the cosmos for billions of years. Each one is held together by the same gravity that created TON 618. Each one will, in its own time and in its own way, come to an end, and in the spaces between them, in the quiet darkness that stretches between the stars and between the galaxies and between the clusters and across the cosmic web, gravity is still at work, still pulling, still shaping, still building, still, after 13.8 billion years, creating the universe. Let that thought carry you now. Let the gentle pull of sleep draw you in, the way gravity draws gas toward the center of a forming star. There is no resistance needed. There is no struggle. There is only the slow, inevitable, peaceful descent into rest. There is one more thing worth saying before we go. If the sheer scale of TON 618 makes you feel small, that is understandable. But consider this. Smallness is not the same as insignificance. A single neuron in your brain is incomparably smaller than a black hole. But a single neuron, connected to billions of others, can compose a symphony, solve an equation, fall in love, or wonder about the nature of black holes 10 billion light-years away. Scale tells you nothing about meaning. The universe is very good at being big. It is not, as far as we know, particularly good at being aware of itself. That is something that, so far, only we seem to do. The universe will be here when you wake up. Ton 618 will still be out there, 10.4 billion light-years away, a silent testament to the power of gravity and the patience of time. And tomorrow, if you like, we can explore another corner of the cosmos together. For now, rest. You have traveled far tonight, from the eyepiece of a 1950s telescope to the edge of a black hole's event horizon, from the birth of a star in a cold nebula to the heat death of the universe. From a number in a catalog to one of the most extraordinary objects ever discovered. You have done well. Now close your eyes and let the darkness be kind. Good night.